and share my screen. I think that should work. All right. Same problem as every week. Okay, that didn't work. Here we go. Okay, I hope you can see my screen now. All right. So in this second theoretical exercise, so the first one really dealing with compilers, we talked about, or we concerned ourselves with lexical analysis. And so we had some theoretical questions with lexical analysis. And you've already seen, of course, there is also a practical exercise concerning lexical analysis. So the first question was about regular languages. And so the first part of this first question was about actually, well, human languages or style of human languages. So you've probably all seen this specific thing, which is called a palindrome. So a word, or maybe a set of words, if you ignore white space and punctuation and capitalization, that is the same when you read it from left to right as when you read it from right to left. So there are simple examples like rotor or madam, but you can also have sophisticated palindromes such as this long Finnish word, which I'm not even trying to pronounce. And the question here was, are palindromes actually regular languages? Now, if you look at these words, you know, when you need to figure out that it's a palindrome, so you need to generate something that's a palindrome using a regular language, then you need to match each character on the left-hand side with a character on the right-hand side. So this is essentially the same problem as when you need to, for example, match brackets in a programming language. So you need to match an opening bracket to a closing bracket. And if you have multiple sets of these, then you need some sort of approach to count them. And we all know, well, regular languages, so DFAs, are unable to count. So to detect these palindromes or to generate some, you need some sort of memory mechanism. So you have to remember the first characters and then somehow replay them in reverse. That can happen using a stack. So essentially, this doesn't work. You need some language that has more capabilities. So essentially another class of language. Regular languages are not enough to detect palindromes. All right, so part B was the question of generating a DFA to actually detect numbers written in scientific exponentiation notation. So you probably all know these numbers from physics, like the Avogadro constant, which is 6.022 E23. So E always stands for times 10 to the power of 23, for example, here. Or the speed of light, which is almost 3 times 10 to the power of 8 meters per second. And here the question was to draw a deterministic finite automaton that accepts numbers in normalized notation without any units, using either the E or the 10 to the power of n notation here. So the power of n, the superscript is missing here. And since we are unable to just formulate this n as superscript, we would write the power of n with this accent circumflex signal here, symbol here. So essentially to be able to write it on a normal keyboard. So one special case for this scientific notation is that the numbers shouldn't start with a 0. So 0 point something was not allowed. So the only permissible digits before our decimal point are 1 to 9. And 1E5 would be a perfectly valid number here. So we could skip all of this after we read the first digit when we read an E. So we could skip to that state here. And then we would read an exponent or multiple digits of an exponent. The same could happen. So this is a bit in small print. Sorry about that. If you read a multiplication sign, and then afterwards we need to figure out the 1 and 0. so 1 and 0 for the times 10, then the exponentiation sign, and then again our exponent. And finally, we could have some decimal point before our exponent. So for example, 2.557 e something, or 2.557 times 10 to the power of something else. So our only accepting state is here at the end when we read at least one digit of our exponent in the scientific notation, but we can also have multiple digits here. I think that wasn't too difficult, right? All right. So part number C of the first question was a bit about thinking about generating languages with certain features, and then getting a bit of practice with using regular expressions. So this question was about creating a regular expression that detects or generates. That's always the same, just the matter of in which way you apply it. So in this way, we say it generates a language over a simple alphabet of just two characters, A and B. And the constraint was that all the strings in this language should contain an even number of Bs. So we know we cannot count in a regular language. So we need to use a trick, and we hinted this trick. So the idea here was really to always ensure that we create two Bs at the same time, or a multiple of two Bs, like four Bs and something. And then we have to ensure that between these two Bs we generate, we can have an arbitrary number of A's. So that one here would be a valid regular expression. So we can have an arbitrary number of A's in front. For example, yeah, just generating that one here. Oops, sorry, that was a typo. A is of course invalid. That's another typo. That should be ABB. Too many typos, sorry. Then we have a B, then we have another arbitrary number of A's, another B, and then another arbitrary number of A's. And we take the clean closure of this so we can repeat whatever is inside these brackets, this pattern here, many times. And of course, for every repetition, the number of A's can be different. So if we wanted to include 0 as an even number of B's, we would actually have to extend this regular expression to also just support an arbitrary number of A's at the beginning without any B's afterwards. We could do this by actually adding a star to the front here. That should actually work. And the other question about regular expressions was, again, to create a regular expression over the alphabet A and B. And here the task was to create strings of a certain length. And this certain length was indicated that the number of the length of the string should actually be n mod m equals 2, with n is the length of the string. So strings and m should be 3, obviously. So in other words, strings in the language should have a length of 2 or 5 or 8 or 11 and so on. And here the trick is actually to generate the two initial letters independently, and then, so that's what we're doing here. So we have A or B, and another A or B. So this means that we can generate all two character combinations of A's and B's. So AA, AB, BA, and BB. And afterwards, we always have this 3-character sequence here, and we can repeat it arbitrary many times, including 0 times, using this clean star here. So we could start with just any combination of two A's and B's, of one A and B, or two A's or two B's, and have 0 of that, or we could add 3 additional characters or another 3 additional characters, and so on. So I think that was also pretty feasible. So the next question was about NFAs and DFAs. So mostly just reiterating and experiencing, the algorithms that we've presented in the lecture. So first, I asked you to construct an NFA to accept the following regular expression. So this is either the string Mars or Miss. And using the construction algorithm, what you do is you first construct simple scanners for each of the included letters. So just a scanner that accepts M and A and R and I and S. And then you can combine these simple scanners here to create the sequences that accept each of these words. And now, since I asked you to create an NFA, it's very simple using the algorithm to combine them. So here we did it with these epsilon transitions here. So we start at this state here, and now the NFA has to choose which of the epsilon transitions it should take. So it needs some method to look in the future. And so it can go from here either to detect mass or Mars or mass or miss. And then finally, all of these single word detections use an epsilon transition to go to the final accepting state. So again, this epsilon transition means you don't need to read any character to go from here to there. But obviously, since we have 3 epsilon transitions, this is a non-deterministic automaton because it needs to choose the way instead of being directed by an input character. So part B was then to convert the NFA to a DFA. So essentially, we start by detecting our end state, which is the epsilon closure of S15, which would be S15, S0, S5, and S10 in our previous diagram. And then we have our combined state here. And we can still increase this further, and that here is the final outcome. That would also be something you would have maybe constructed by hand if you were asked to. So we always start with an M because all of our 3 words start with an M. And then we have 2 words starting with an A, so Mars or Mars. So we split after the second character red to distinguish between Mars here and Mars. And then finally, if we read an M and the next character is an I, we know we have to read miss here, here, and then finally we have the accepting state over there. So this is all a bit dry and boring, I know, but luckily it's only part of the most boring part of compilers, so scanning, because it's relatively simple, but still you need to do it correctly to implement a compiler. So question number 3 was to use DFA minimization, so to use the table method or Myhill-Nerode method to minimize the DFA that was given here. And you should show the performed steps, the changes to the table, and the final minimized DFA. So here we have a DFA just starting with S0 here. And from S0, we can either read an A, and then we end up in S1, which is already an accepting state, or we can read a B, which ends up in S2, which is also an accepting state. So we can already figure out the first 2 words in our language. That would be just a single A or a single B. But in an accepting state, you don't have to accept. You can go further if there are following characters. So for example, from S0, you can go read an A and another A. So that would not be a valid word because we're not in an accepting state, but we might be reading yet another A. So if we read 3 A's here, we end up in an accepting state again that accepts an arbitrary additional numbers of A's and B's. And now you probably noticed this diagram is very symmetric, so you could do the same by starting with B. Then if you have a B, you switch over to there. The same as if you have a B in S1, you switch down to here. So essentially, I think it should be obvious that there are some ways to minimize this. So we start with partitioning our graph and just entering the partitioning information in our table here. So we construct a table with all the pairs of states of the DFA. So this table would be symmetric. So essentially, we just need to fill in half of the table, excluding the diagonal. And first, we distinguish between states that are accepting states, so like that one here, that one up here, and the final state on the right, and the other 3 states that are not accepting states. So if one of the states is an accepting state and the other is a non-accepting state, then we add a mark to our table at the combination. So for example, we have S0 here, we have S1 up here. So we enter a mark here at the combination of S1 and S0. Same with S2 and S0 here. So S2 is an accepting state, S0 is not, and so on. So when we do it for all of the combinations of our state, we see, okay, there's only a smaller number of free entries left, and we have to do something about the free entries. And to do this, we start again with our table we just generated in the previous approach. Now we look at all the unmarked pairs only. So this one here S1, S2, this one here S0, S3, that one here S0, S4, and finally S1, S5, S2, S5, and that one over here S3, S4. So if there are any unmarked pairs, P and Q, then what you do is you look at the delta functions of these. So if you have a pair P and Q, so that the delta function when you enter a character, so the following state for both P and Q when you enter the same character X, if this already has a mark, then you also mark this original P and Q. So you look at all the empty ones, and then you figure out using your graph or, well, your table representing your DFA, what are the subsequent states, so the transitions that are taken given a certain character here. And if you find that these follow-up states here already have a mark, then you also mark the state you were going from. And so we could find that one here. So S1, S5 for an A would be marked. That one here also for a B, S1, S5 for a B. And these two down here would also receive a mark. So essentially we have to add a number of marks here for the combination of S5, S2 and S5, S1. So we have these ones down here now. So we are left with 4 free positions. So we're going through the table again. We again go through all of these 4 positions here. And now you might think like, what does this change? Well, what has changed before is that we have 2 additional markings here. So these 2 additional markings here could make a change in the conditions actually to add a mark to these 4 remaining open positions here. So that's also a possibility for optimization. So if you know that you only added these marks and you want to implement this in a computer, you could actually use this knowledge because you know the other ones have been unaffected. So step 3, repeat the same steps until no more markings can be made. And in step 3, we find out that S3 and S0, as well as S4 and S0, also have to receive a mark here. So we add these 2 marks. And then we go through it again, repeat until no more markings can be made. So we only have 2 combinations left here, which are marked in green and purple. And we figure out, okay, if we go through all of this, no more markings can be made. Well, that's fine. So we can terminate our algorithm. And then these unmarked elements here actually give us information about which states are equivalent here. So we know in this combination S1, S2, that state S1 is equivalent to state S2, away, the one up here and the one down here. And state S3 is equivalent to state S4. So the one up here is equivalent to the one down here. So we see very nicely that we have this symmetry, which we can actually reduce. And we reduce this by adding both input characters here to our transition. So whereas in the original graph, we had an A going up and a B going down, we can just combine this to AB because both S1 and S2 originally are accepting states. So we can combine S1, S2 to this new accepting state S1, 2. And the same for S3 and S4. So these are both non-accepting states. That's why you did the partitioning in the beginning, actually, to not accidentally mix up accepting and non-accepting states. And so we have this new combined state S3, 4, which again has transitions A and B, because we can reach this using such an A transition up here, or a B transition from top to bottom or from bottom to top. And finally, well, we have this AB going from both S3 and S4 to our final state S5. And in S5, we then return to itself with an arbitrary number of A's and B's. So of course, this is something you don't want to do by hand. This is something you want a computer to do for you. And obviously, this is pretty easy for a computer to do. So writing an algorithm to do this should be, well, relatively simple. I dare not saying trivial because, well, people thought a long time about really getting this right. But, well, just using the description in the algorithm, it should actually be able to write something like this. So those were the theoretical exercises for this week, or that were due this week. We had some hands-in for the theoretical exercise. I think about 11 groups handed something in, so that's very nice for optional exercises which don't have to be handed in and are not paid part of the grade. I hope it wasn't too boring. Let me check the chat again. First, I'll stop my recording. Whoops. Whoever created this user interface